All right, I want to talk more about these unit step functions. So we did a few. Here it is. A unit step function is a 0 or a 1. But then you multiply it, and there's a picture of it. It's a 0 until it gets to a, and then it's a 1 the rest of its life when t is greater than a, greater than or equal to a. And then I dealt with some constants, so I had some step functions, but we do it with other functions. So here's a t squared multiplied by u t minus 2. So I want to show you a mistake real quick. This is a mistake. So sometimes I think, oh, this is a t squared. It's a parabola, and it gets turned on at 2. Okay, so it's a 0. That's until it gets to 2. It's a 0, and then it gets to 2, and then it's a parabola. But that's not really right. Hold on, that's not right at all. You know, forget the unit step function for a second. It's a parabola, t squared, that's over here. You know, the parabola t squared is over here. There's 1, there's 2. When x is 2 or t is 2, y is 4. So there it is. You know, but hold on. Now, if I pay attention to the unit step function attached to it here, it's multiplied by it. So it is this t squared, but it's off until you get to 2. It's a 0 until you get to 2. And then when you get to 2, it's turned on. But what's turned on is what's there. So this whole part of it is turned off. So and this too also, by the way. So the parabola is turned off, and it's a 0 until you get to 2. And then it gets turned on, and it's that part of the parabola. It's that leg of the parabola when t is greater than or equal to 2. So that's okay. But as opposed to that, there is this, and this happens a lot. We have, when I see stuff like this, I'm going to say the phrase, the argument of the function matches the argument of the unit step function. That the argument of the function is the input of the function. So the input of the function is t minus 2. When the t minus 2, or the argument of the function matches the t minus 2, that's kind of classic. That is what I started to draw a few minutes ago. That's a parabola that's shifted over 2. But it doesn't get turned on until 2. So that's this. It's a 0 until you get to 2. But then it's the parabola gets turned on. So that's that classic picture. That's what's going on there. You know, I'm going to keep talking. I'm going to get some more examples here for you. You can digest those a little bit. They're different. There is this. There's this one. 4 sine t, so this is a function. It's called the function of t. 4 sine t attached to the unit step function t minus pi, minus 4 sine t attached to the unit step function t minus 2 pi. Yeah, that's okay. So let's see, what is this? Again, I sort of want to draw a picture of it. What I could do is write it as a piecewise function. I've taught you that you can call this, but I don't know. I like to draw it as I think it through. That's what I do. So, so here I am. Let me see here. So it's a sine function with an amplitude of 4. It's a sine function with an amplitude of 4. That looks like this. You know, it's kind of cool. Just draw a sine function with an amplitude of 4. But hold on. Let's see. Its period is 2 pi, so there it is. It does one complete cycle at 2 pi. That means it's here at pi. There it is at 3 pi and 4 pi and so forth. Okay, that helps. It helps to know what you're doing a little bit. Now, what is this unit step function going to do? So, remember, it starts off as a 0. Yeah, so it's a 0 until you get to pi. Then this gets turned on. Okay, all right, so this is not even here. It's a 0 until you get to pi. It's a 0 until you get to pi. Then the function gets turned on, and it's this part of the function, I guess. Okay, and then it would be on forever. It would be on forever, except something happens at 2 pi. what happens at 2 pi is we turn on this guy, which is the negative of this guy. And so I end up technically turning him off. So at 2 pi, the rest of this gets turned off. What did I just do? At 2 pi, I turned on the negative. That's actually, I guess I turned on this function. And when you add it to that function, they cancel each other out. You could talk like that. Boy, I mean, this gets added to this. It's a 0. Now it's a 0. I don't want to do that visually. It's a 0. So this is turned off. This is all turned off. And we're a 0 the rest of the way. Huh, that's interesting. I mean, and that's a technique. I mean, if you're trying to just turn on a little blip of a function for just a little second, then it's off for a while. It gets turned on at pi. Then we turn him off at 2 pi. We turn on the negative of the function. Okay, I want to erase this and do another example. Okay. Here's one. This is a 6. What did I want to do? I guess I'll try cosine. 6 cosine of t minus 6 cosine of t u t minus pi over 2 plus 2 cosine of t u t minus 3 pi over 2. Huh. That's kind of strange. All right, that's kind of crazy. Again, what is this? So I like to talk about it visually. Again, I could turn all this into a piecewise function, which we all kind of are a little more familiar with. We understand a little bit better. I do that visually is what I do. So here I go. Remember, this is this technique where there is no unit step function here. So this is just a nice cosine function. This starts off as a cosine function. There is no unit step function here. It starts off as a cosine function, and amplitude is 6. Cosine starts up here and dives through here like this. And by the way, it dives through here at pi over 2. It comes back through at 3 pi over 2. And it's back here at 2 pi. That's one complete cycle of just a cosine function with a period of 2 pi. Amplitude is 6. Okay, so there it is. Wait a minute, that's him. Now what happens? Oh, at pi over 2, we're turning on the unit step function. And the unit step function is now a 1. But it's attached to this, which is multiplying this by 1, and it's the negative of this, which essentially is that's how we turn him off. So at pi over 2, he's turned off. And that's true the rest of the way. The rest of the way, it's turned off. The rest of the way until we do something else. I mean, this is now on, and that's turning on the negative of this, which is turning him off. So this is done. It's a 0 the rest of the way until something else happens. Oh, something else does happen. At 3 pi over 2, we're turning this on. Okay, so we would be a 0 the rest of the way, but at 3 pi over 2, we are turning on 2 cosine t. That's interesting. That's a little cosine function with a different amplitude. And what? Hang on. That's a cosine function with a different amplitude. Oh, but it's getting turned on right there. Okay, so this part of it's off. This part of it's off. It's got an amplitude of 2, but it's getting turned on like a cosine function would. And now it has this amplitude of 2. And then it just goes forever? Yeah, I guess so. There it is. Boy, that's weird. That is weird. I make up some strange problems. Huh. Starts off on for a minute, gets turned off for a little while, and then this comes on. Interesting. Okay, a couple more things to say. of course, we're going to get to Laplaces, and so I'm just going to lay this out for you. We'll have to practice some of this probably in the next video, but I want to just preview this idea here. So we got a rule that says, how do you do the Laplace of a function f of t minus a that's multiplied by a unit step function ut minus a? So this is our first Laplace rule for unit step functions attached to some function f of t minus a. And the rule is this. It's e to the negative as times big F of s. You know, and what I like to do is try to interpret that for you. And to me, it means this. When you have this unit step function, okay, that kind of spits out this. That's where this comes from. That's where this e to the negative as just kind of indicates that this came from a unit step function. And then, even though the argument t minus a has to, for this rule to work, the argument t minus a has to match this t minus a, all you're really doing is you're doing the Laplace of f of t. I hope that you remember the notation. The Laplace of f of t is the big F of s. But to use the rule, it has to be an f of t minus a, but then you're not doing the Laplace of t minus a, you're doing the Laplace of f of t. That's what big F of s is. So that's funny. This rule, this is rule 56. You know, you don't have to memorize it. It's in your tables, but it's how to do the Laplace of a unit step function attached to some function where the arguments match. And then that's the rule. We should practice a couple, but I wanted to point out there's another rule. There's the rule when the arguments don't match. It's the rule for g of t that happens to be number 57. And it's when you have a g of t and a unit step function t minus a. So we have a unit step function, but this time the argument doesn't match. And you get this e to the negative as. That just sort of tells you that comes from this unit step function aspect. And then it says, do the Laplace of him, but not the Laplace of him, the Laplace of him as if he was shifted over t plus a. So now you're end up doing the Laplace of this thing. And then you got to do that Laplace. I mean, I don't have a name for that. That's not big G of s. The Laplace of him would be big G of s. That's not what it is. It's the Laplace of him. So that gets a little tricky. This gets a little tricky here at the end of 7.3. A lot of good homework problems to practice. I want to say this. So there's two kinds of Laplaces we can go moving forward. It depends on if the argument matches the unit step function or not. But when you do Laplace inverses going backwards, you always use 56. Okay? If you do a Laplace inverse going backwards, you can't really make this work. This is hard. I can't get that to work. So I'm always using Rule 56 when I'm trying to do Laplace inverses and go backwards. All right, I'm going to have to do more examples, but you can start on some homework, learning the unit step function. Thank you.